And welcome, Mindsetters, to this grade 12 session of Learn Extra Live. I hope you guys are ready. You've got your pens and pads out and you're going to make some notes. On that note, I'm Ty and I'm here with Phil, who's going to be taking us through today's session. So, Phil, what are we doing today?
We're talking about cells and we're talking about batteries. This is a section which grade 12s really struggle with. But this is for 11s and 12s. There's a little bit of redox for the 11s, cells and batteries for the 12s, so everyone should be watching.
All right, cool. So while Phil makes his way across the board, Mindsetters, as I always say, make sure you get your posts on the page. Let me know if you've got any issues, if you're lost here, if you need help. Because on top of that, I need to give away these awesome calculators and this labeler from Casio. Make sure that you guys post on the page. Guys, as I also always say, that feel free to post anything that will help out another mindsetter, whether it's a quote, if it's something that will be helpful for the lesson. Guys, feel free to post pictures, anything, because the best posts get to go in for these awesome prizes. And on that note as well, I want to say, mindsetters, if you see a mindsetter in trouble or if someone needs help, don't always leave it for us, because we might not always get to those questions. So make sure, if you know what the answer is, help a mindsetter out. But on that note, this is where I want to say quick shout out to Liberty. Thank you for sponsoring. And this is where I hand over to Phil. Phil, take it away.
Thank you so much, Ty. Okay, well, what I've got in front of me is a whole bunch of cells and batteries. Now, just a reminder from that grade 9 lesson that you forgot all about, the difference between a cell and a battery is when I've got a single thing like this, I no longer call it a battery. This is actually called a cell. That means that it's one connection of plus and minus. When I put several of these cells together, I make a battery. So now, just a reminder, the next time that you actually see somebody using the word battery to describe one of these, oh, it doesn't seem to want to stand on its own. Okay, but one of these is actually called a cell. Now, this is a battery. The difference between this and this is that a couple of these has actually been squeezed inside here, but they've been a slightly different type. Now, what I'm going to be doing is I'm going to be showing you how we actually get some of these readings on the front of here. If you pick up one of these, you'll actually find that there's in fine print on here, and it's very tiny, so I'm actually going to show you on this thing, is you can actually read some very important information about your cell or your battery. If you take a look at the front of this battery, there's important information. I want you to see that there is a reading of the voltage. This is a 4-volt battery, and it's got a cell capacity of 2.1 amp hours. So you can actually see this. Now, if you guys are not busy chatting on your cell phones, I actually want you to take out your cell phone batteries and see if you can find these numbers on your cell phone battery. Now, that battery itself might be a battery, might only be one cell. You can actually see this information. You can see a voltage or EMF, and you can see the cell capacity. Now, what I'm going to do is I'm actually going to be doing a reading on this voltmeter to check the voltage on one of these cells. So what I'm going to do is I'm actually going to apply the electrodes of my voltmeter over here, and let's actually test to see what the voltage is. Now, I'm going to ask you a few questions about why I'm reading the voltage that I am, and if I do this, I'm actually going to find a voltage which is not quite the same as the battery markings on the front there. I'm actually going to find that there is 3.57, which is lower than the 4 volts which I find on there. So I'm going to do this again. If I put my battery reading over there, I get almost 4 volts, but not quite. So what I'm going to do is I'm going to ask you to think about why that voltage might be different to the reading on the front. I've got a few cells over here. Now, you'll see actually a different voltage. So what I'm actually going to do is I'm going to read the voltage on one of these as well, and let's actually start to see what I get. So now I'm going to apply my voltmeter over there. Let's actually switch those around so you get a positive value. So I'm actually going to read there, and I get a voltage of 1.4 volts. Now, there's quite a difference between what's contained inside this cell and this battery. Inside this battery, I've combined multiple cells. Now, the problem is that this is all confusing, and there's a whole bunch of numbers everywhere. How can I tell if it's a cell, if it's a battery, and all of these terms? I'm going to explain the major differences behind these today. So what I'm going to do is I'm going to hand back to Ty just very briefly. He's going to start talking to you about the Facebook page and some of the things that we're going to be talking to you about. And I'm pretty sure that he wants to give that calculator away. What do you say, Ty?
Yes, definitely. So on that note, Mindsetters, make sure that you keep posting. Because as I said, it's beyond just us posting randomly, or not saying posting randomly, but it's beyond just us just saying post, because it's supposed to be a platform for you guys to help each other out, talk, and use for notes. So if you don't post, Sometimes you might think, oh, question is silly, but someone else might have the same question. So when you post, you could actually help someone out a lot. So make sure that you guys post. And yes, I'm still looking out for the person to give away these awesome prizes to. But on that note, this is where I hand over to Phil. Phil, take it away.
Thanks so much, Ty. Okay, cells and batteries. Now, what we've noticed, every time I mark questions on cells and batteries, I find that there's major misunderstandings of cells and batteries. So we're going to take it apart piece by piece. And grade 12s, you know me, I like to give you a little bit of a challenge. And I've actually given a question to Ty, and I'm going to ask him to post that up on the Facebook page. So that challenge question is one of the first things that we're actually going to get into. Right, and there it is. Okay, so my challenge question for today. Guys, write down the information, and I've actually modeled this on that cell, which I actually showed you, or actually that battery rather. Okay, so a 2.1 amp hour cell is at 4 volts. Okay, so those are the readings which I actually got off the side of the battery. If I read those pieces of information, is connected to a 4 volt cell, to a light bulb, and it gives out 2 watts of power. Now, there's a couple of options. It tells me that the cells last either 6 hours and 30 minutes, or 4 hours and 18 minutes, or 4 hours and 30 minutes, or 1 hour and 3 minutes. Okay, guys, you've got to be able to figure this out by the end of the lesson. So if I connected that battery, I'm actually going to reach out a shot, and I'm just going to get that battery again. So this was exactly the battery which I'm talking about. This battery over here, 4 volts with 2.1 amp hour capacity. If I connected this to a 2 watt light bulb, how long would the light bulb stay lit? In other words, how long would the cell last if I have a 4 volt battery at 2.1 amp hours? Okay, so here we go. Here's my combination of cells together. This is the exact cell which is inside your challenge question. Now, if I connect this to a 2 watt bulb, how much is it going to be giving out for? So in other words, I want to know the time that it's actually going to last for. Bit of a challenging question. It's going to require you to listen very, very carefully and very closely to what we're talking about, but there's my hint. Okay? So there is information in today's show that will actually tell you about how to figure out about this battery and how long it would last if I had a 4 volt 2 watt light bulb. So let me just highlight the important information, the stuff which you're going to use to calculate, and let's get into the lesson today. Okay, so again, cell capacity, 2.1 amp hours, there it is. So there's the information about the cell capacity. I know that the cell gives us 4 volts. So because it gives out 4 volts, there we go. I'm going to connect it to a light bulb, which when it's connected to 4 volts, it's going to give out 2 watts. Okay, very important information. Now, all we've got for option A, B, C, or D is how long this all is going to last. Now, let's get into the magic. Let's start talking about batteries and cell, and let's power up. Okay. So now what I'm going to be talking to you about is going to require a little bit of prior knowledge. Okay, so guys, this is the stuff that you should be revising before you do batteries and cells. There's a little bit of grade 10, a little bit of grade 11, and even a little bit of grade 12. I need you guys to know what dissociation reactions are. That means that when I put a salt into a solution, it's actually going to split into positive and negative ions. You guys have got to know what you're doing with ions before you start to balance redox reactions. And that's the next part, oxidation and reduction. Guys, chemical systems requires you to know chemical change. You cannot learn chemical systems before you learn chemical change. Now, batteries and cells are great, and they're an easy way to score marks, but only if you know oxidation reduction. That means that I need to know redox from grade 11 and 12. What's inside there is electrolytic and electrochemical cells. We're going to be talking about those interchangeably. I'm going to expect you to know what they are. But I will explain them for anyone that's a little bit lost and go, oh, electrolytic, electrochemical, I'm all confused. I don't know what to do. Okay, I'm going to help you piece by piece. Okay, so now I know that I need to know electrolytic, electrochemical cells. Those are an application of redox, and that's an application of dissociation reactions as well. So these are the 3 sections that I go and advise that you study before you even start with batteries and cells. Okay, but now you guys don't have time to do that, so what we're going to do is we're going to get on with today's lesson, and if you're really, really confused, I want you guys to get on that page. Ty's busy there. I can see him feverishly typing away. Okay, he's busy answering your questions and hopefully getting some of them to me, and we can actually fix your stuff together. Now, most of the time, what I've actually done is actually gone and looked on the page, and you guys have actually sorted out each other's problems, which is great. That's what the page is there for. Okay, so let's climb into the stuff. Why do we have cells? Well, why do I have a battery inside a remote? Why do I have a battery inside a car? Why do I have a battery inside any device? Well, why do I need a cell inside my cell phone? Okay, now those those two words are not that related, but a cell phone uses cells to give it power. Now, I use this. Now, please make sure that you know these. A cell provides chemical potential. Please, this is what a cell does. They often ask this question, why do I use cells? A chemical potential energy is entering into the circuit. I need that potential energy to power the screen, to power the LEDs, even to power a board like this. I need some sort of electrical energy. Now, the great thing about cells is that they're portable. Now, this board needs to be plugged in, and it relies on Eskom giving us power. Now, if you got a battery, you're free, and you can move around with whatever you've got. If you've got a cell phone, if you've got an MP3 player, you've got an iPod, whatever you've got, a laptop, all of them have got cells. And the way that they carry around that power is they carry around that potential chemical energy. Now, this means that they are spontaneous. Now, please, I need to emphasize what these words actually mean. Okay, so spontaneous. If you are a spontaneous person, that means that it happens without any sort of help. That's going to happen automatically. Now, exothermic, if you guys remember from grade 11, exothermic. Well, thermic is starting to talk about temperature, starts to talk about energy. Now, exo means to give out. So that's the other part of this, is that it gives off energy. Two very important things about a cell which I need to know is that it gives off its energy and it starts without me helping it. So spontaneous means that it's going to start without any help, and then exothermic, it means that it gives off energy. That's the energy which I need. So I just want to make sure that people understand that this energy is electrical energy. It's not heat. Now, if your battery is making heat, it's probably not doing its job properly. Okay, so this is electrical energy, which we're talking about here. I hope you can actually read my terrible writing. I'm writing with my finger. Okay, so now I've got chemical potential energy. It's changing into electrical energy, and that is the purpose of a cell. I can carry it anywhere I like. I'm free to go wireless. So that means that I can do a spontaneous exothermic reaction inside the cell, which allows me to have energy on demand. Okay, so that's why I've got cells inside there. What we're going to start off with is some primary cells, but before we do that, I think we're going to take our first ad break. What do you think?
I think so too.
Okay, and it's going to give us a chance to get you guys writing down some of this stuff. There's a lot of information coming. We're going to divide up the show into primary and secondary cells. I'm going to talk about cell capacity. It's going to get all busy in here. So to give you guys a little bit of a chance, and I actually want to read what people are doing on this challenge question.
Okay.
I'm pretty sure that people are starting to answer. Just a reminder, guys, that your challenge question answers are no good without an explanation.
Exactly. That's exactly what I was going to say on this next link.
Absolutely. Okay, Ty, is there anything you want to add before we take that ad break?
I think that we're good to go for now for the ad break. So, as I said, mindset is if you're going to answer the challenge question, I will not consider it unless there's an explanation for your answer. So, now that I've put it out there, hey, get to work. See you after this break. Welcome back, Mindsetters. I hope you had a nice little break there and you went and did whatever you had to do. You went to the bathroom, you had to go speak to mom, you had to go speak to dad, your brother, your sister, and now everyone has to now stop irritating you, and now you have to pay attention and focus with your pens and pads out and ready to make notes. But on a quick side note, I just want to say happy birthday to Munaka. Hey, thank you for being on the page, and I hope you're enjoying the show. But on that note, this is where I hand over to Phil. Phil, take it away.
Thanks so much, Ty. Okay, well, great that you guys are giving us a little bit of feedback. We're going to start talking about the cells themselves. Okay, so now the question before the break was, well, why would I be carrying one of these around inside my pocket? Well, it would usually be inside something which needs a little bit of energy. Now, first thing that we're going to start talking about is primary cells, not because the word means first, but because primary cells are a very particular type of cell. Now, primary cells, these are cells which can only be used once. Now, most of the time, when you start putting in one of these, the sad thing is, eventually it's going to go flat, it's going to give out all of its energy, and I've got to throw it away. Now, this is one of the things which makes a primary cell a bit of a problem. Primary cells are very useful. I've got the chemicals inside here, and I'm going to show you how the magic happens in a moment, but primary cells can only be used once, and that's one of the major issues of a primary cell, is that primary cells are usable only once. Okay, now they are electrochemical, or galvanic cells. Now, please, I want you guys to make sure that you actually know the meaning of these words. Electrochemical or galvanic cells actually do something very, very specific. electrochemical or galvanic cells. I'm going to use the words interchangeably throughout the show, so you need to know that a galvanic is an electrochemical, and electrochemical is a galvanic. These are the same thing. Okay, so electrochemical or galvanic cells, these do something very specific. They take chemical energy. So what they're doing is they're going to take some chemicals inside them. I buy the chemicals in the shop, and I'm going to take chemical energy, and what I'm going to do with it inside that cell is I'm actually going to take chemical energy and change it, like I said, into electrical energy. Now, that is a one-way process for these guys. Once they've given out all their chemical potential energy, all of it's gone. I actually need to throw away these cells. Now, that's a bit of a pain. That means that I've got to buy an awful lot of these things. So if I'm constantly doing this and I'm constantly switching these out, that is one of the major disadvantages of primary cells. Now, we're going to dedicate a little bit of time later on in the show to primary cells and why this particular cell is going to run out and cause problems. Now, I've chosen this particular one. I'm not actually using this one because this one I've already used. It's used up its chemical energy, and there's very little of its cell capacity left. That means that I've used up the chemicals inside here. That's a bit of a problem. I've actually got to take this cell, and now I've got to throw it away. Now, the problem is that you cannot actually throw these guys away safely by throwing them into the dustbin. You should not dispose of primary cells inside the dustbin. What you can do is take them to a recycling center. Now, a whole bunch of you are saying, you know, I can't do that every time there's cells. Now, what I want you to do, and I want to encourage this is your environmentally friendly tip, is to actually take these cells and take them to your local Pick and Pay or your local Woolworths. They've actually got recycling bins directly outside their shops, so they will do the hard work for you. So every time you see one of these and they're flat and you've got to get rid of them, please put them inside a plastic packet and actually take them down to your local shopping center, because they've actually got a place to safely recycle these, and they can actually change them back into new batteries. And that means that the chemicals inside here are not going down deep into the ground. You might say, well, that's not my problem. It is. Now, one of the biggest problems in the world in terms of batteries going to landfills is that some of these have actually got an element called mercury inside. Now, mercury gets inside landfills, it leaches down into the borehole water eventually gets through to the river eventually gets into you, and you don't want that happening. So make sure that you put these batteries in the safe place, and that is not the bin. You should not be throwing these inside the bin. Even when they're finished, please dispose of them properly. Take them to a recycling center, and Pick and Pay and Woolworths have actually got bins outside, so they do all the hard work for you. Okay, so there's your green tip for today. Once I've changed all the chemical potential energy into electrical energy, I'm going to take this and safely dispose of it. Now all these extra little bits and pieces and tips, all these extra pieces of info, you might say, okay, well, do I have to remember that? Well, every time you write a paragraph about these batteries, it's actually useful information to know these extra pieces, because this is a very common place for them to ask learning outcomes 3 questions. That is where science applies to the economy, to society, and to the environment. Now, by law, we've got to put some of those learning outcome 3 questions. You guys better know a little bit about the environment, about society, and the economy to be able to answer those questions. Learning outcome 3, very often you cannot study. So what we're going to do is give you a couple of tips. Battery recycling is one of those tips. Very often I've actually seen that as one of those things. Okay, so now these primary cells, they can only be used once, and that's one of their major disadvantages. Also, how is that going to affect me economically? That means that I've got to go out and I've got to buy one of these again. So that's one of the major problems with primary cells, is each time I want to use them, I've got to go buy a new one, I've got to buy a fresh one, eventually they're going to go flat. Okay, now when I say that a cell is flat, it's given out all of its chemical energy. And now it's all in the form of electrical energy. I've used it all up. Okay, so now let's take a look at this type of cell. Now, this particular type of cell is very, very useful. It's called the Electron Shell cell. Okay, now something else which this is actually called is called the dry cell. Now you might say, okay, well, why wouldn't it be dry? Okay, well, the problem is that you've actually got chemicals inside here which need to react. And the magic of the dry cell is that it actually uses chemicals which are made into an electrolyte. But that electrolyte is in the form of a paste. Okay, now if you start to think about toothpaste, it's around about the same consistency. It's kind of solid, it's not really a liquid, but it's going to stay inside the tube. Now the same thing inside this cell of mine. If I take the cell and I open it up, And you should never do this because there's harmful chemicals inside. You can cut yourself. I've actually cut myself before doing this. If you open up a cell, you'll actually find that there is an electrolyte inside there, which is almost the same as toothpaste, except it's this really dark black color. We'll talk about the color in a moment. But let's look at the other pieces of one of these cells. Now, this picture, I've actually asked Ty, and I think, Ty, have you posted it up to the page?
Well, it's actually loading now. So.
Oh, fantastic. Okay, a work in progress. That's great. Okay, so now you're going to see a picture of a cell which is like this, where I've got two very different pieces. I've got this tiny little piece up at the top, which has kind of got this extra little knuckle up at the top, all right, and that is my positive electrode. Now, that is linked up inside, and you can actually see this picture as if somebody cut this open. I've got a carbon rod attached to that, and that is the positive terminal. So that means that I make a plus sign on the top there. If you go look at a battery, and I actually want you guys to do this with me, is if you go look up at the top, I can actually see a plus symbol right up at the top of this battery, and that's where the carbon rod is attached. Now onto the zinc case down at the bottom, you'll actually find this flat piece down at the bottom. That's where I find my negative terminal. So there it is, and I think it's actually on your diagram. The diagram I've sent through to Ty has actually got these labels in it. But now that top little piece, that little bump, is where there's plus. And the zinc case, the bottom piece, that's where I find my negative. Now you might say, okay, well, plus and minus. How do I actually figure this out? Well, that tiny little bump up at the top, how does all the plus collect there and how does all the minus collect there? Well, we've got different chemical reactions, and this is where your redox is actually going to become very, very useful. Okay, so let's go and take a closer look at some of the chemistry which is happening inside the electrolyte of this. Now, just a reminder of what an electrolyte is. An electrolyte is a conductive substance through which ions move. Okay, so let's actually just write down a note there. So now, an electrolyte over here, it is a conductive, it's usually a liquid. So we can find that it is conductive, and that is usually in the form of ions. So they are conductive, and it's conductive ionic substance. So that means that there's plus ions and there's minus ions moving around inside there, but an electrolyte is a conductive ionic substance. That's found in between those two plates. Now let's try to figure out how we get plus and how we get minus. Well, this is down to some redox. And most of this redox doesn't actually happen on your redox table. So what I'm going to do is I'm going to show you how they're going to give this to you in your final exams, and I'm going to show you exactly what they expect you to do with it. Well, there they are. There's a huge amount of information. Sad to say that it's really, really tiny, but this is how it's going to look in your final, and it looks so confusing. Okay, I start to notice a whole bunch of information. Oh, goodness, I've got zinc, and I've got MnO2. I'm actually going to ask my producer to put it up on screen if he hasn't. I've got zinc in my first reaction over there, and it's producing a E0 potential of negative 1,04 volts. And the other one is producing a positive potential. Well, this is starting to give me a little bit of a sign as to what's going on here. Now, inside your exam, they will give you exactly something like that. Now, what they expect you to do is to label and then combine these half reactions, which is what we're going to do today. So let's label them first. Zinc is going to zinc 2 plus 2 electrons. The electrons are on the right-hand side. That should tell me something. That means that I've actually got a process called oxidation happening. There is a loss of electrons. So this is oxidation. I know that oxidation is happening to the zinc. And this is one of the reasons that a battery actually stops working after a while. The zinc can no longer oxidize because it's actually formed a layer of oxide on the inside. So oxidation starts to occur. So what we're finding is that there's a loss of electrons, is oxidation, and also, if you remember from electrochemical cells, oxidation always occurs at the anode. Okay, so that's quite important. So oxidation, which occurs at the anode. Well, I'm pretty sure that you've guessed that the other reaction, even though it's so complicated, it's all about the electrons. And in the second equation, I'm actually going to highlight both the electrons. The electrons were on the right when there's oxidation. When there's reduction, the electrons are on the left-hand side, and that makes that into reduction. So there we go. We know that reduction is occurring, and if you know your electrochemical cells, reduction always occurs at the cathode. It's absolutely vital that you know that. Okay, now the thing which is common to both of these is that the first reaction is making electrons. So now electrons, I've got to start to tie this together inside my mind. That means that I'm producing a whole bunch of electrons on the one side of my cell. Well, if you've got a whole bunch of extra electrons, what you've got is a negative charge. Electrons are negative. So if I'm manufacturing electrons like I am in my first reaction, I'm going to find that a whole bunch of electrons are actually going to wait there to escape and go through a circuit and come back around to the other side. Now, my other reaction, which actually happens at the carbon electrode, uses up electrons. I can see that electrons are going in. So what we're going to find is that at that other electron where electrons are being used up, I'm going to find positive. There's too few electrons. So I make electrons here, they go through the circuit, and they come around to my other side. So electrons go out of the negative, around through the circuit, and into the positive. Now that is electron current. It is not the same as conventional current. In grade 10 you learned that conventional current goes from plus to minus. But what actually happens in most cases is that electrons go from negative around to plus. So I know that there's going to be some questions about that. Okay, now down to the redox part, which I'm really excited about. We're actually going to add these two reactions together. I want you to do this with me. Now, if you've written down the half reaction, the zinc goes to zinc 2 plus 2 electrons, and we've got an E0 cell voltage. That is my first reaction. That made 2 electrons. Now, my reduction reaction, lucky for us, also used 2 electrons. So all I need to do to balance this out is to cancel out my electrons. There we go. I'm canceling them out. Now, if I write everything on the left-hand side together and everything on the right-hand side together, what I get is a balanced or net ionic reaction. Now, it's so long. All I've done is I've combined everything on the left-hand side together. So what I'm actually going to do is I'm going to highlight them in the same colors. So now everything on the left-hand side, so it's going to be in green. Okay, so there we go. A whole bunch of green. And I've got green all over there. So I've added all of those together. That's how I do this. Now everything on the right-hand side of the arrow, I'm going to highlight in yellow. So let's just make sure that that all goes together. So I've just got zinc 2 plus. The electrons are going to disappear, remember? All right, and there it is. It's a huge, huge, huge amount. But now what I'm sure that you've noticed is that nowhere inside here have I actually got room for carbon to react. Remember that one of the pieces of Electron Shell dry cell is actually that carbon rod which is attached to the top. Carbon is not reactive. Carbon is inert. That means that it's not actually participating anywhere inside these reactions. So now I've got my balanced reaction. And, well, now what I've got to do with this is I've actually got to do a little bit more of a step. There's something else which I want to show you. Something which they can ask you to do is to use the electrode potentials of each one. Now, how on earth do I actually manage to do that? Well, the answer is actually quite simple. I've got to use my redox knowledge and know how to combine these two half reaction voltages. I know that at the zinc, I've got negative 1,04 volts, and on the other side, at the carbon electrode, I've got positive 0,5. How do I actually stick these two together? Well, let's actually do an E0 cell calculation together. So this is how much I can actually expect the battery to produce, or the cell rather. So E0 cell, remember, is E0 cathode. Now that's actually a theta, but just for shorts, very often it's called E0. Okay, so E0 cathode minus E0 anode. Well, lucky for us, we actually spotted which ones those were. So what I'm going to do is my cathode, remember, was positive 0,5, there we go, volts, minus, now this is why I use brackets, minus a negative voltage of 1,04 volts. And what comes out here is positive 1,54 volts. That voltage sounds kind of familiar for a very good reason. That's the voltage of one of these cells. This is a 1.5 volt dry cell. If I go take a look on any one of these cells, you'll actually see that it's 1,5 volts. The reason for that is because I used the paste inside here. It is of the cell type. Now, it doesn't matter how big I make the cell, it's still going to be the same EMF. It's still going to have the same voltage. Now, there's two factors which do change this EMF. Now, those are the concentration and the temperature of the cell. So now I can find that temperature is one of the factors of those. So temperature is one of the factors which affects EMF. Now, one of the little tricks, if you're using one of these cells, is if you want to get the last little piece of energy out of them, is you can actually heat them up in the sun for a very short amount of time. The warmer they are, the more EMF they're going to give out. So they might give you a few more minutes of power. If you're stuck in a tight spot and you don't have any more of these replacement cells, the way to get a little bit more EMF is actually to pump up that temperature, and you get a little bit more power out of these. So temperature is one of the factors. The other factor, and this is the most important one, is the concentration. Now, the concentration of the electrolyte. The concentration as the electrolyte runs out is actually the reason that this is no longer giving out 1.5 volts. If you're watching carefully earlier on in this program, this one only measured 1.4 volts. That means that this cell is about to die. It no longer has any energy left. So I've only got 1.4 instead of 1.5. That means that this cell is relatively flat. You'll notice that any one of these cells, if you measure anything less than around about 1.45 volts, that this cell is on its way out. It no longer has the required energy that I need. Okay, well, I'm busy talking like a motor mouth here. I'm hoping that people are listening.
No, they're following along.
Okay, do you think I should carry on? I think I should. What do you think? Can I handle it?
I think maybe we might want to take a break, because I'm sure you're going to introduce another subject into this.
Absolutely. Oh, okay. Before we do that, let's just recap. There's a whole bunch of info. Okay, so just to revise what we were talking about. Okay, well, this is a huge amount of information on one board. So what I'm going to do is I'm going to talk your way through this. Okay. First of all, we identified my oxidation reaction. The way that we did that was by spotting that electrons were coming out on the right-hand side. That was happening at the zinc electrode. So that's all the way at the bottom here. On the other side, we saw that there was actually something happening. Our electrolyte, manganese dioxide, that's the black stuff inside here. It's a very dark black color. Plus ammonium chloride. And now I'm pretty sure that you guys have noticed sometimes when these batteries get kind of damaged or inside a device which has got these, you'll find a white substance. Now, a lot of people seem to think that that is an acid. Now, it's not so much an acid as a salt, and that is ammonium chloride. That's actually a salt which is leaking out of the electrolyte here. It's not toxic. It's not going to poison you. In fact, ammonium chloride has actually been used in cough syrup. So please don't be afraid of it. That little white fluffy stuff is not going to harm you. Just wash it off with a wet cloth. Okay, so manganese dioxide and ammonium chloride, those form the paste inside here. What happens to them is they actually get reduced and eventually run out. Now, one of the things that actually starts to happen inside here is that paste can dry out, and that's one of the reasons really old batteries no longer work. So once I've done my oxidation of zinc and my reduction of manganese dioxide, I've now got a combined electrochemical cell. Just a reminder that they can do this to you. You need to identify which one is oxidation reduction, and that gets you which one is the anode and the cathode. Why would I want to do that? Well, that allows me to figure out how much voltage I can expect from one of these cells. And that's very, very important. If I know the anode, if I know the cathode, I can do an E0 cell is equal to cathode minus anode. And that gets me a voltage. And I actually managed to predict, without looking on the side of the cell, that this one can give me an EMF, an electromotive force, of 1.54 volts. And that is it. Just remember your two factors which can affect the performance of this battery. One is temperature, because the hotter it is, the more EMF it gives, and the concentration. As the concentration of electrolyte goes up, the more EMF. But now the problem is when it starts running out or getting too cold, the EMF drops in both cases. I think it's time for that break. What do you think, Ty?
Definitely. But also wanted to make a note out there, because I've been hearing a lot of people saying, oh, I want to go explore with our batteries. I was like, but guys, you have to be still very, very careful.
Absolutely.
Preferably do it at school with the teacher supervising, because this stuff can get dangerous. And yeah, some of the liquids in there are toxic.
Absolutely.
Exactly. So mindset is be careful. But on that note, make sure you come back, and we'll see you after this break. And welcome back, Mindsetters. Okay, now right. Here's where I have a problem. Because as I said earlier, I can only choose a winner who's posted their answer with their explanation. I'm still getting singles here, like A here and a B here, C here, a random D somewhere. Mindsetters, I need the answer with it. And this is a quick draw. So the first person to post the answer and the explanation is going to win these awesome prizes. So I'm going to be looking out for that person right now. So make sure mindset is you get posting, get posting, get posting. But on that note, this is where I hand over to Mr. Phil.
Thank you, Ty. Okay, well, now what we're going to do is we're going to divert our attention now to secondary cells. We started talking about primary cells, and I told you the primary cells are a problem because every time I use them and they're finished, I have to throw them away. Now, the reason that I've got this guy here is this is a torch battery. Now, one of the major problems with torch batteries is I use a torch and I'm out camping, and I can't just go out and buy a new battery when I'm out camping or I'm outside and I'm by the sea or whatever. I cannot just replace this. So one of the really cool things about this is that the torch that's attached to this has actually got a solar panel. The cool thing about secondary cells is you can recharge them. Now, this is kind of like a really tiny car battery. We were talking about car batteries in the break. And one of the things that you need to know about secondary cells are full of nasty chemicals. This particular one has got two very toxic things inside it. It's got lead and it's got some sulfuric acid inside there. So please, please, never open this. Never open a car battery. Like Ty says, please be careful. Ask your teacher first. Don't go ripping apart batteries. You can create a fire. You can poison yourself, cut yourself. Please be careful.
The amount of risks are dangerous. So make sure, safety first.
Absolutely. Okay, so as Ty says, safety first, okay? And if you want to do this, ask your science teacher to do it with you there because they know some of the risks. Okay, so some lead, some acid inside here. Acid can burn your hands, and the lead is very, very toxic. Okay, but now let's take a look at the science behind why secondary cells are so amazing. The lead acid cell itself is the one which they like to ask the most. Now, let's just write down why it's called a secondary cell. These ones can be recharged. We can reverse these ones. We can use these many times. And that's pretty cool for my pocket because it does mean that I can use this, recharge it, and use it again. So I can reuse these. So these can be recharged. Okay, so now the really cool thing about these is I can connect these up to some voltage supply and I can recharge these. Now you might have guessed that the one inside your cell phone at home is a secondary cell because a secondary cell can be recharged and recharged and recharged. Imagine buying batteries for your cell phone every single day of your life. That's going to be a real pain. So you can see why secondary cells are the stuff to use inside something which is going to be used quite often. Okay, so rechargeable cells. These are great, but now, as I said, it's got two very important pieces which I don't particularly like. Let's just move that out of the way so that you can actually read this. Okay, so now I can recharge these. Now, the two major problems with a lead-acid battery are the lead and the acid. Okay, now they might ask you, why is a lead-acid battery a bad thing to put inside a landfill? Once a lead-acid battery doesn't work anymore, we've recharged it like 400 times. Now what do I do with the stuff? Again, take it to the recycling center because the lead and the acid are environmental and health problems. Lead is a neurotoxin. That means that it affects the nervous system inside my body. If I had lead poisoning, what starts to happen is I start to get pains inside my arms. I start to feel like my arms are on fire. I can even go crazy. Okay, so lead is a heavy metal toxin and finds its way into water systems. It kills fish and eventually can kill people as well. The bad thing about lead is every piece of lead which I absorb inside my body actually stays inside my body for life. The lead which goes inside there finds its way into fatty tissue, and most of the fatty tissue inside your body is actually between your ears, inside your brain. So lead tends to accumulate inside your brain and poison your brain. Bad stuff. So make sure that you don't open this up and give yourself some lead poisoning, please. That's going to stay with you for life. Now the acid inside, let's actually mention which acid that is. That acid is sulfuric acid. Very, very cheap, around about 1 rand a liter. This stuff is really mean and nasty. It burns holes in clothes. It burns holes in you as well. Okay, so please, lead and acid, very dangerous stuff inside a lead-acid battery. Now, they might actually ask you questions about the dangers of using a lead-acid battery. Now, let's just recap those. Lead itself is a heavy metal toxin, poisons the nervous system, and the acid H2SO4 can cause burns. It's very, very corrosive and it rusts things and it causes lots of problems there. Okay, so now what I've done is I've asked Ty, and I think Ty's busy posting. I saw him a little bit busy on his laptop over there.
Mm-hmm.
Okay, so there's a man at work and he's posted up a picture of a lead acid battery up onto the cell. Now, I've actually taken a look at one individual cell. So this is a lead acid cell. When I put multiple cells together, then it becomes a battery. So let's just take a look at what's going on here. We're starting to take a look at one electrode and then the other electrode. So let's just highlight the important pieces of information inside here. Now, it's worth memorizing what goes on inside these because the Leclerc Shell dry cell is one of the questions which they ask all the time. And here's the other one. The lead acid cell is a prime target for your matric finals. And guys, just a little bit of a hint, those are 2 months away. So start getting on this stuff. Start memorizing, start making notes. Okay, so the lead or Pb electrode, that is the one which is going to make the anode. Now, I've got PbO2, which is lead 4 oxide. And that is my cathode. So let's just highlight what those are. So I've got Pb as an anode. I've got PbO2, which is going to make up the cathode. So one where oxidation is taking place, one where reduction is taking place, and the electrolyte between them is the acid. So what I've got in between them is actually a salt bridge, and that is H2SO4. So that goes right in the middle there. Now, one of the problems with this type of battery is you can't actually leave these batteries too long because the H2SO4 actually damages these. This is why you can't run a car battery flat. It's because the H2SO4 causes damage inside those batteries. This is one of the reasons that sometimes batteries don't work for a very long time. I'm pretty sure that you've been around a car that tries to start, you hear them, and the car is trying to start, and one of the major problems is that the H2SO4 has actually damaged the battery inside that car. Now that H2SO4 is some very important stuff. It is the electrolyte between the Pb and the PbO2. Okay, now let's take a little bit of a look at those reactions. How can it be asked this cell inside an exam? Well, the very nice thing is if you manage to follow what we were talking about earlier on, it's exactly the same. Now, I'm going to take a look at the negative and the positive plate, and we're going to see what goes on. So let's just highlight the important piece of information. There's a lot of it on the screen at the moment. Pb, there it is, at my negative plate is going to react with PbO2, and that is that lead peroxide, or is it lead 4 oxide? So some people even call it lead dioxide, so it's got several names. But there are your two materials. So what's going to happen is lead is going to go on to produce 2 electrons. Remember what I said about electrons being on the right-hand side? That means that this first one was oxidation. So let's just label it as we go along. Okay, so I'm just going to abbreviate here because otherwise we're going to be short of time. Then the second one is going to be my reduction. And they can do exactly the same thing to you and ask you to calculate the E0 cell. That is if they provide you with the voltages. I showed you how to do that a little bit earlier. So just one last thing to do with these two is to add on these electrons. So let's just highlight where the electrons are before I cancel them out. So there we go. We've got electrons on the right, electrons on the left. That means that we can cancel them. There's 2 of each. So let's cancel them. So there we go. Electrons in my oxidation cancelled out. Electrons in my reduction, which are cancelled out as well. Now let's combine them. Let's stick everything together. Let's make my teacher happy. And let's get marks in the back pocket. So now what I'm going to do is there is my combined chemical reaction. There it is. Okay, so I'm combining lead with lead peroxide and some H2SO4. And out comes a whole bunch of lead sulfate and water. Now just something interesting to note is when you change my H2SO4 into water, the electrolyte gets less dense. And you can actually measure how full a battery is charged by how dense my electrolyte is. You can actually put in something called a hydrometer, and it can actually measure the density of the electrolyte inside there. Now, if it's got a density of 1.3 grams per centimeter cubed or more, that means that your battery has a high charge. That means that there's lots of sulfuric acid inside there. If it's close to 1, it means that it's almost all turned into water and your battery is flat. So this acid can actually tell you how full that cell actually is. Now, one last tiny little bit before I put you out of your misery for the challenge question is I'm actually going to start calculating my way through these things. Just a piece of advice when you're starting to talk about battery capacity. Here is my equation. So let's just label it as we go. So now Q, you should have seen from grade 10 before. Now, we're going to use it slightly differently. This is called my cell capacity. Now, your cell capacity is a type of charge, and that's why I call it the charge. It's because it's how much charge this battery can store. I is the current, which, if you remember, is measured in amperes. Now, here's something different. The time which you use in this calculation is no longer in seconds when you start to talk about cells. This time is measured in hours. That's why I measure battery capacity, and you saw this earlier on, in amp hours. So my cell capacity over there is measured in amp hours. Okay, well, that's quite interesting. Well, what now? I've got a battery capacity, and we're starting to work towards our challenge question now. I told you that you had a battery capacity of 2.1 amp hours. That means that if I supplied a current of 2.1 amps, I could do that for 1 hour. A different way to look at this is that I can supply a current of 1 amp for 2.1 hours. Now, I want you to play around with this. Anytime you get the current and the time to multiply to give me a number of 2.1, that means that I can combine that. That's one way to calculate your challenge question. That can give you the time in hours. So just a bit of a hint there. Another equation which you might have found useful is this one. This one is also from grade 10. You might have seen it in a slightly different form. So let's actually put up the original form which you might see on your information sheet. That V is equal to W over Q. So voltage is the work done per coulomb of charge. Now this work is the amount of energy inside there. So what we're going to do is we're going to take a look at the capacity, and we're going to start to take a look at the work, and we're actually going to start to see what is going on here. Okay, I've got W, and that's equal to V times Q. Now let's actually start calculating the bits and pieces of our challenge question. So I'm going to use this equation, and we're going to start working towards my challenge question. Now, for those of you that started guessing, I want you guys to write this down, please. I want to figure out which one of these are actually going to do this. So the first thing which I'm going to do is I'm going to figure out how much energy is actually stored inside my cell. Energy is work that that cell can do. So now there's two very important pieces of information over here. Let's identify them for you. So I've got Q and I've got V. Initially, I can actually figure out how much energy is inside that cell, and that's very important. Now, let's write this all down. So W is equal to V times by Q. So let's put in my V. My voltage is 4 volts. If I multiply that by a Q of 2.1 amp hours, out comes something which I don't really recognize all that well. I get 8.4, but now the question is, what are the units if I don't use Q in coulombs anymore? If I've multiplied volts times by current times by hours, well, volts times by current gives me watts multiplied by hours. So I get a unit called a watt hour. This is a way that I measure the cell energy. Now, you guys need to be able to use this. It's the same equation from grade 10, except the unit is no longer a joule, but is a watt hour. Now, the question is, what does this actually mean? This means that I could give out 1 watt for 8.4 hours, or I could give out 8.4 watts for 1 hour. Now, that starts to ring a bell. Wait a minute, what was I trying to do initially? What I was trying to do initially was I'm trying to power a 2-watt light bulb. Well, let's actually start to take a look at how we can actually use this. That's a measure of power. Okay, so now a third equation which we're actually going to start getting into is that power is equal to work over, and here's where you're going to get your time from. All right, let's actually write that in correctly so that you can actually see what's going on. There we go, that's a T. Okay, so power is equal to work over time. Which do I want? Well, I know that I want time out of this equation, so I'm going to manipulate this. Let's get time on its own. So this time is equal to work divided by the power. So let's put in our numbers. We know that the work that the battery can actually do is 8.4, and I'm going to divide it by the power which it's giving out currently, which is 2. If I start to calculate these and I start to divide these, what I'm actually going to find is something quite surprising. If I get 8.4 and I divide it by 2, I get 4.2. Okay, now if you start to take a look through your answers, something really peculiar is going to start happening. I can't be 6 hours, so that's answer A out of the question. I can't get the cells last 1 hour and 3 minutes, can't be. So it's got to be option B or C. Now, which one is correct? Now, please, 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 just make sure that you pay attention to the idea that I've actually got a decimal happening here. I've got 0.2 of an hour. That doesn't mean necessarily 20 or 30 minutes. What I've got to do is I've got to say 0.2, and I've got to divide it by my 60, and what I will actually find is that my correct answer over here is that that works out to be 18 minutes. There we go. And answer B is the correct one. So for those of you that got answer B and explained it through to me and actually got those decimals through back into minutes, this is your correct answer. So correct answer for today's challenge question is B. Now, we've got a tiny amount of time. Are there any questions, Ty?
So far, nothing exactly. I'm scanning through the page right now, but my computer has decided that its battery cells is having issues, so it's slowing down on me.
Okay, cells are running out there.
Yeah. But right now we don't have much. But as I've been saying to the mindsetters, make sure. I'm sure a lot of you are like, oh, but why don't I get the prize? It's because you didn't put the answer, your explanation, next to your answer. And guys, I always say, if you're gonna answer these questions, make sure it's the symbol and your explanation for you to qualify, for you to win these awesome prizes. And it goes to the first one to post. Simple as that. So mindset is, I cannot stress to you enough, make sure that you do this properly. But for now, I don't see any questions. So
no problem. We're going to do a little bit of a recap then.
Exactly.
Okay. So just to recap what we're talking about, primary and secondary cells, the types of questions that they can ask. Okay. Primary cells are those which I can only use once. And I'm just going to grab them again. Primary cells are like this, very much like the Electron Shell cells. And let's just bring up that picture. So the Electron Shell cells, these types. When you start to take a look at secondary cells, let's actually start to bring those up. Secondary cells like these. These are ones which I can recharge. So they can ask you a lot of questions, learning outcome 3 questions about why these are bad and these are bad as well. But both of them have advantages and disadvantages. Make a habit of putting up a table at each one of your sections. But folks, as always, we're running out of time. And I think I'm going to hand back to Ty just to say goodbye to you guys.
All right. So on that note, mindsetters, thank you. Make sure that you guys keep posting. I'm scanning on the page. I'm trying to find my winner. But yes, I swear I will make sure that once I find that person. So make sure mindsetters, that you keep chatting to each other. And as I always say, always make sure you make notes of these lessons, because I know, especially you matrix, that you guys have exams coming up in the major. But I want to say best of luck and best studying to you. And yes, I'll be scanning for the Casios, for the winner of this Casio calculator and this. And on that note, I also want to say thank you to Liberty. So guys, as I wanted to make sure, also I just want to say Manaka, is it Manaka? Sorry, my apologies. But yes, happy birthday to you. And mindsetters, keep using the page. It's something for you guys to use as a platform, as I keep saying. And don't forget the website, www.facebook.com/learnextra. And as I keep saying, tell a friend to tell a friend to tell another friend to make sure that they get on the page, and then tell their friends to get on the page. So mindsetters, I just want to say thank you for joining us in today's session. And from Phil, I'm sure he says thank you to you too. So for me, this is where I then sign off. I'm Ty, and I'm going to say thank you for joining us, and see you next time.